AC circuits. Unfortunately, it's going to be on a different AC circuit, and I'm not sure I'm going to cover that. Definitely, you should do self-study on it if you're interested in the topic. It's very useful, especially if you think of becoming an experimental physicist or experimental scientist. Knowing how to deal with AC circuits is actually very useful. Rather is due no extension because the reader is really down through. He's from Canton. He could go back more. He's a future grad. You know, he almost finished his classes and whatnot. There's no final, I suppose. The session is Wednesday. As I posted on the courses, this is going to be on the chapter 1 to 5, and then it's going to be on 5 to 9. And so there's an overlap there. Any questions? What is everybody here? Still on vacation. But yes, to continue on our discussion last Tuesday, so we were talking about our circuit. Studying its resonance property. So this is all we're going to do for this lecture, and hopefully this will take the next half an hour or so. I'm not going to talk about the driven one. If you drive it with an AC source, right? There's a whole another chapter. Most of chapter 8 is actually on that, right? If you guys are interested, I can actually give a lecture, separate lecture that you're not responsible for. I don't know, maybe next week. On AC circuits. Right? Because it can be useful, depending on what your interests are, it can be very useful. But you know, I'm not going to talk about that, but so this is only the homogeneous part of the equation that we'll look into. So this is the Kirchhoff law around the circuit. Current is defined to be positive in that direction. No AC source. Like that, right? Since Q can be written as C times V, I can also write this differential equation as a differential equation for the voltage. This is the voltage across the capacitor C. Okay, and the analog here, as we discussed on Tuesday, is a mechanical analog where you have a driven harmonic oscillator, right? Driven single harmonic oscillator, and the solution is given by a King exponential times sinusoidal function, okay? And omega here is given by square root of 1 over LC minus R squared over 4L squared, and then alpha, which is the decay term, is given by R over L. Okay, I can rewrite this equation. This is going to be written this way as a square root of omega naught minus alpha squared. Okay, where omega naught is 1 over LC, and then alpha is just that alpha. Okay, so in general, at least in this case, or in most cases of interest in AC circuit, you have a situation that's slightly damped. What does it mean? But that solution is only true if omega naught is actually greater than alpha. Right? Otherwise, the plug inside the square root is negative, and then that would be a completely different solution. But in most cases of interest, omega naught is actually much larger than alpha. Okay? So in that case, this is true in most cases because that term alpha, which is R over 2L, is small, okay? Meaning that R is small. That happened graph the voltage across the capacitor as a function of time. There's an envelope, right? That decay as 1 over e to the minus alpha t, right? And then there's a sinusoidal form. Like that. Okay. And then the characteristic time of the decay, right, which is that time constant for the decay tau. Characteristic time. It's just 1 over alpha. Okay. This is loosely speaking, by the way, because I will use tau for something else later on. And then the period here between oscillation, this period is 2 pi over, right? And in this case here, the situation of the lightning dam means that this period here is much smaller than tau. Okay? 2 pi over omega is much smaller than tau. Right? You have many oscillations as this decay. Okay? Any questions so far? And I can also choose the time, right? Choose the t equals 0 in such a way that I can always write v t as e naught e to the minus alpha t cosine. Okay? So I choose time properly in such a way that I start at the top of the sinusoidal. Okay. Questions so far?
Can you go over what the characteristic time is?
Yes. So if you look at here, okay, I should probably do this backward, right? So the solution is given by an exponential decay times cosine omega t, right? If we choose time properly, right? So this exponential decay is this envelope. Right? There's an envelope that decay. Right? It's multiplying a cosine omega t, right? Which is the sinusoidal. Right? So really the function is this, right? This is just the envelope.
Yeah.
And the envelope decay has e to the minus alpha t, and then there's a characteristic time. It's 1 over e time. This is the time it takes so that the function here drops to 1 over e. The function v dropped to 1 over e of its original value. So 1 over e is about 1/3. So when this happened around here, I suppose, right? This is 1 over e of the original value v naught, right? So this is tau. Tau goes all the way here.
Why is that important? And why
It's a characteristic for the exponential decay. Right? It gives you a scale of the function.
Okay.
Yes. Yes. So where are we here? And then the situation where you have a lightly damped condition is such that this oscillation, the fast oscillation here, is happening at a time scale that's much smaller than the characteristic time of the decay. You have many oscillations in 1 over e time of the decay. Okay. So that is the condition that we're looking at. Any question on this? No question on this? So let's look at the current. The current is just I on the V is just C3, right, with a minus sign. That's how you define it. And so it's minus C VT, because Q is just CV. Okay? So I need to differentiate that function. When I differentiate the function, I get omega C V naught e to the minus minus alpha t minus omega sine omega t. Of course, you use this cosine omega t times minus alpha into minus alpha t. Right? I'm just differentiating this function v here with respect to time. Right? It's a product of exponential and cosine. So when I differentiate, I get this two term, right? And rewrite it, it becomes omega c naught e to the minus alpha t sine omega t plus alpha over omega cosine omega t. Okay? So in this case here, I have a sum of sine and cosine, right? So if you remember from your geometry, sine of A plus B, you remember? This is meant 1A or 1B. It's sine A cosine B plus cosine A. Right? Okay? So in this case here, I can write this as a sine of omega t plus v, right? And it becomes sine omega t cosine v plus sine v cosine omega t. And if I compare this and that, right, with some constant that I'm dropping, you'll find that tangent v is equal to alpha over omega. Okay? Since omega is omega is right here. Omega is much larger than alpha, right? This is the condition that we're looking at. Then tangent v is close to 0. Okay? I can basically ignore this term. Okay? And the current is going to be just given by omega c naught e to the minus alpha t sine. Okay, I'm just ignoring the tangent v term, which is small. Okay, so as you see, well, one more step. So if I look at the voltage drop across R, right? VR is just given as a function of time, it's given by the current times R, right? Okay, so this becomes just then WC R V naught e to the minus alpha t sine omega. Okay, so if you compare the time dependence of the voltage across the capacitor and the voltage across the resistor, one comes with the cosine omega t, right? And the other one is sine omega t. Okay? I can draw it again here. Use the envelope. Right? This is across the capacitor. This is across the resistor. This is function of time. It's actually like this. This is a first use a PowerPoint something. So just to make sure. And yeah, I'm probably not scared of this property, but you get the idea, right? There is a lag here. The voltage across the resistor lag. You see by pi over about 90. Okay. So the voltage across the capacitor is ahead by 90 degrees. comparative voltage across the
That one,
resistor.
there's the voltage of the capacitor?
That's the voltage across the capacitor.
Okay.
Right? Okay. And this is the voltage across the resistor. Okay. Okay. Any question? Okay. And how about the voltage across the inductor? Let me erase this. The voltage across the inductor as a function of time is given by minus L dt, right? This is the from Faraday's law, right? This is the EMF, this is minus the flux, the rate of change of the flux. Okay? So, when you do the math, you get this is equal to minus L, and then you take the form of the current and differentiate with respect to time, right? I don't have time for all the algebra, but you do the same thing here, you'll get this is going to be equal to, if you all do all the algebra, this is going to be equal to minus V naught e to the minus alpha t cosine with the minus sign. Just take the formula for I and differentiate it with respect to time. Okay? And you have to make the approximation that the alpha over omega. Right? So you ignore all the small little phase lag because of the alpha over omega. Right? And as you see here, because of the minus sign, this is the envelope, the function goes like this. So the voltage across the inductor lags dc by R, or 100. And in general, this is always true. And the reason I emphasize this is because this is the least I could do if I'm not considering any discussion on the driven AC circuit. In any AC circuit across a loop, driven or not driven, right? Vc is always the head, right? And then Vr is lags by 90 degrees, okay? And Vl lags by 180 degrees relative to okay. They form a triad of some sort. Questions so far? So next, let's look at the energy dissipation, right? What is the energy dissipated in this process? What happened is, remember, if we used to just have L, C and L, right? Then you have an oscillation between electrical energy and kinetic energy, right? You introduce a resistor here, right? Then there's a power dissipation, which is I squared R. Okay. And let's look at the total energy. Total electrical energy as a function of time is just the electrical energy is only stored in the capacitor, right? It's just 1/2 CV squared. Okay. So if you do all the math, you'll find that this is going to be equal to 1/2 CV naught e to the naught squared, right? E to the minus 2 2 alpha t, because now this is v squared, right, times cosine squared omega t. Okay. We did this discussion a little bit. So we'll have, in this case here, you have an envelope, right? At an envelope at k, the envelope at k has to be minus 2 alpha t. Then with the factor of 2, because you have a square, right? So the energy has to decay faster. Okay? And then there's a cosine term here. Right? This is a cosine square, so it's only positive. Okay? And then there is also the term that's the magnetic energy as a function of time, and this is energy stored in the inductor. Right? And it goes as 1/2 Li squared. Okay? Substituting the formula for the current, right? After you will run all this approximation that I have got this, then you will find, after doing all the algebra, maybe I should do one step of the algebra, 1/2 L omega c v naught squared, right, e to the minus 2 alpha t sine squared omega t. Right? And if you look at this term here, right, remember omega squared is equal to omega naught squared minus alpha squared, right? Since omega naught is much larger than alpha, then omega is approximately equal to omega naught, right? And omega naught is equal to 1/square root of LC, right? This is the natural resonance frequency of the LC circuit without the resistor, okay? So when you do that, you get this equal to 1/2 C v naught squared e to the minus 2 alpha t sine squared. Okay? The total electrical energy is just UE. That's UE, right? And that just becomes equal to 1/2 C v naught squared. The sine square omega t plus cosine square omega t giving me 1. Right? So this is becoming equal to minus 2 alpha t. So the total energy decay is a function of time. It goes like that. E to the minus 2 alpha t. Okay?
Does it look the same for the graph of the energy stored in the L? The inductor? Is it just
oh yeah, the inductor, I should probably throw it too, right?
Mm-hmm.
Then there's an envelope, and there is a sinusoidal function that goes like that.
Okay, yeah, so they end up just canceling for that.
Yeah. No, but when you add them,
Yeah, so they
right,
make.
then it just becomes like that.
Right.
Okay. Question so far? There's a lot of algebra, you know, but hopefully everything is obvious. So let's calculate, the power dissipation. Let's calculate U total. Power change of energy, of energy change. And when we do that, this becomes, if you differentiate U, right? E to the minus 2 alpha t, right? You get minus 2 alpha t, minus 2 alpha, 1/2 C v naught e to the minus 2 alpha t. This is equal to minus 2 alpha v total. This is rate of energy dissipation. Or energy change. Okay. So let's see. Any questions so far? Let me rewrite this equation. There is a reason I want to do all this, right? Let me rewrite this equation. Let me write T over the total. And that becomes equal to 2 alpha, right? Therefore, if I write U total over P is equal to 1 over 2 alpha. Okay? But if I look at the form of the energy drop as a function of time, right? As a function of time, there is a characteristic time. 1 over E time tau. This is the tau that I want to use, right? I'm going to use, right? For U to drop to 1 over E of its original value, right? That tau is equal to 1 over 2 alpha. Okay? Because if I substitute the T equal to tau here, right, then I have 1 over E. Okay. Right. So at time equal to tau, which is one over 2 alpha, the total energy is dropped to 1 over E of its original value. Right? Okay. So this is equal to okay. So here I come to one of the most important concepts in the discussion of lightning down resonator, right? I don't know if you've seen this a lot before. But there's a concept called Q, which is defined to be omega times tau, right? And this is actually also called the quality factor. For lightning jam oscillator. So you can think of this as the number of oscillation, right, in the unit of radian, right, that it takes for the energy to drop to 1 over E of its original value. Omega is the frequency, and T is the time, right? This gives me the number of cycles until I reach 1 over E of the energy drop. Right? Okay, so that's the easiest way to think about this. That's a number of cycles. For total energy drop 1 over E of the okay. That's it, right? But often, instead of writing it this way, you see it in literature, right? You write it as C tau is just U total over T. Right? So often in literature, you see Q written as omega times U total over T. In fact, this is the definition for Q. But this is no more than just that. Okay. And the higher Q is, means that the more lightly damped the resonator that we have, right? The more oscillation. Say if I have a tuning fork, right? I hit it and then let it ring, right? And the higher the Q factor of the tuning fork means that the more oscillation I get before the whole thing goes away. Right? So, and the same case here, when you consider RLC circuit. Because you can think of this as a tuning fork also, as an oscillator. In this case, it's an oscillation between electrical and magnetic energy. And it decays away because of R. Right? And the smaller R is, the higher Q you have. Right? As you see that this Q here is equal to omega over 2 alpha. Right? Because tau is 1 over 2 alpha. Right? So here, what is alpha? So a lot of algebra here. Alpha is R over 2F. From the solution of the differential equation.
Is this the same Q that's involved when you have like resonance and makes like the
Yes.
different?
This is the same Q as in 7a when you're talking about the quality factor for a mechanical oscillator. It happens everywhere. Q is one of the most important figure of merit, or one of the most important parameters that you use anytime you consider a resonator that's lagging down, meaning that there's a lot of oscillation before the energy decays away. Right? In particular, a case of interest for me, at least, or things that I'm usually dealing with often, is a laser resonator. In a laser resonator, Q is also a very important parameter. So in that case, there's just a slight version here. If I have a laser value, it's like launch back and forth between the resonator, right? And then some of them exit, and this is how you get your lightsaber, right? You get the light coming out, right? So the Q factor here in this case, it's not, I put the parentheses here because it's not exactly the same, right? There's two definitions. One is called Q, the other one is called finesse. Right? In this case, I'm actually talking about finesse, which is basically equal to the number of oscillation of photons experience inside the cavity before it exits. That's also Q. Meaning that there's an energy in here, right? And which is the total energy, and then there is some portion that goes away. Right? That's your dissipation. Right? So same thing. Here you have U over P multiplying omega, right? And that gives you the Q factor.
So can you do that with anything that's dissipated?
Almost anything,
like gas in your car?
any resonator system that has a small dissipation. You can always define a Q. Right?
Mm-hmm.
But in the case of of interest right now, for an LRC circuit, Q is just omega over 2 alpha, where alpha is R over L.
So does a laser operate like a driven AC circuit? Are you just increasing the speed of the photon and it goes back and forth when it exits?
No, it's not. It's not exactly the same. It's the same. It's actually a resonator.
Okay, so when it resonates, then it's an exit.
There is a resonator, right? And the resonator, first of all, you have to pump it, right? So you have an active energy. Then you pump it with something else, right? This is your driven. We don't discuss that in this case, but the last half of chapter 8 talks about the driven AC circuit, right? So there is a driving EMF, right? And the analog for that in a laser is that there is an active medium that pump the population inversion that leads to stimulated emission of radiation in here, right? But once you have that, you have a resonator. Right? So this is the same as your C and L, right? But the mirror is slightly lossy. At the end, one end of the output coupler of a laser is slightly lossy, so you allow light to exit. And this is the analog of your resistor. And you can analyze a laser that way, semi-gravity. But that's beyond the subject of our class. But with that in mind, this is the end of chapter 8. Right? At least for our class. I encourage you to actually study driven AC circuits, driven AC circuit as much as you can, because it's very useful. And in light of this discussion about the laser resonator, let's move on to chapter 9. So this is the last week. How many weeks has it been since we studied ENM?
I thought we
8 weeks,
have
right?
been
8
studying.
weeks, right?
Oh.
Because there was a 4 weeks of thermodynamics, right? So this is what we know so far. Right? This is a view, right? So what do we know? In differential form, we know that the divergence of E is rho over epsilon naught, right? To save time, I'm not going to write the integral form. We also know that the divergence of B is equal to 0, right? This is Gauss law. And lately, we've been learning 2 more equations, right? One of them is the curl B is equal to mu naught J, right? What law is this? This is Ampere's law, right? And the last one, the curl of E is equal to minus dV. Right? And this is called the Faraday's law. So that's it. This is what we've done in 8 weeks. Summarized in something that you can write on a t-shirt. Except that if you do that, it's wrong. Right? It's still wrong. So even after 8 weeks, something is missing. Something is missing. Maybe something quite fast. First, let's consider the following. You have a capacitor. It's discharging to a resistor. Right? So you charge the capacitor, right? You connect it to a circuit. Current will flow, right? This current flow, if I just look at the loop here, right? Let me just put this up. Let me put this up here. I have a wire, current is flowing. And if I look at the loop C, right? Then from Ampere's law, is equal to mu naught I enclosed, right? And I can consider the surface here as just a simple surface that's flat with a loop. Okay? So, and this surface is being pierced by the current line. Okay? And then Ampere's law tells you that this is what you have. Right? Okay? But something is still amiss, right? Because you know that the surface that we use can be any surface bounded by C, right? So if I suppose I actually take my surface to be something like that, right? Take a super thing, right? You glue it there, right? And then you get something like this. And you can close half the capacitor with that. Right? Now what do you have, right? Again, this is a loop C, but this is surface S prime, right? Okay, so the line integral over loop C of PDL, right, is equal to mu naught I enclosed. But if I use S prime, instead of S, there is no piercing of current. Right? No current. No current. Something is wrong.
Could you repeat what S prime is? Is that a surface?
Yeah, S prime is a surface. So S is a surface just if I have a loop, right? If I have a loop, S is just a surface flat with a loop, right? So the current flows through, right? So Ampere's law gives you that equation, right? But this thing, if the line in the growth of field has to be meaningful, right? Then it should be independent of any surface. Right? In particular, I can choose a surface, right, that envelope half of the capacitor. Right? Think of this as this looks like some kind of a container or a phase, right? Look at the phase, right? That can envelope one half of the capacitor plate. Right? And in that case here, then there is no current piercing through the loop or through the surface. Right? So this is equal to 0.
Why would it be no? Why would it be no current facing through it?
Because there is no current here, right?
Oh, in the-
the
oh, I
current is
see.
only on the wire, right? And the wire doesn't pierce through that surface.
So what would it do to go?
So something is definitely not right, right? Also, this is the reasoning given by Purcell. Even Faraday reasoned that way too. Or not Faraday, sorry, Maxwell, right? Faraday didn't this. But of course we know better because we know relativity, right? From relativity, recall what is the transformation that you have. E prime is equal to E. Prime is equal to E, right? Okay. And E perpendicular is equal to gamma E perpendicular plus beta plus B. Perpendicular minus beta plus B. So if you look at this equation, there's a lot of symmetry here, right? In fact, there's a lot of symmetry. Between E and B. Right? It says if you interchange E and B, you get something similar, except for a minus sign. Right? Let's ignore that for now. Okay? Well, if you look at your Maxwell equation, let's just look at this. This is okay. This looks kind of symmetrical, except this is 0, and there's a charge density here, right? Let's ignore that fact for now, right? Let's look at the character of the equation, right? Here I have a curl of B is equal to J, but I have a curl of E is equal to minus the rate of change of B, right? Right? So it's not symmetrical, right? You would expect that you would have something like this. If you have, then you must have something like that, right? Plus or minus, we don't know yet. Some constant. We expect something like this from relativity. Okay. And let's see if we actually can understand this better. Of course, you have invariance of charge and conservation of charge, right? This is the continuity equation. What does it tell you? the gradient of J has to be equal to minus 0. Okay? Or the integral equation of this is J plus A, right, over a closed surface, right, has to be equal to minus the total integral of rho dV. If I have a volume, the rate of change of the charge inside this volume has to be equal to the flux of current coming out, right?